One of the interesting and important applications of trees, and particularly binary trees, is what's called a binary search tree. Trees are a very efficient way to store data because the search times to find things can be very short. Essentially, it's on the order of log base 2 of the size of the amount of data stored. So a binary search tree is a useful tool, and we're going to look at how to build a simple binary search tree, and then you can hopefully see how it can be expanded. A binary search tree is a binary tree where every parent, which includes the root, is larger than its left child and everything in the left subtree, but also smaller than everything in its right child and everything in the right subtree. Okay. Now, there are some strategies to taking a list of data and coming up with sort of the best, or what we call a balanced, binary search tree. But we're going to just start with the basics here, and we're just going to take these numbers in as they come. Now, sometimes you'll see words used as the elements of a binary search tree, and you use alphabetical order, but essentially anything that can be ordered can be constructed into a binary search tree. Okay, so we're going to start with the number 10 over here, and we're going to always make the first data value we see the root of the tree. Okay, then we're going to go to the next number in our list, and we're going to try to find a place for it in the tree. Okay, so we're going to compare it to the number 10. Is it less than 10? Yes. Is there anything less than 10 already? No, it's empty. So we're going to put 5 into that position right there. Okay. Now we come over to the number 7, and we again start up at the root, and we ask ourselves, are we less than 10? Yes. So then we're going to ask ourselves, are we less than 5? No. If we're not less than 5, we're going to have to move to the right, find an opening, and put the number 7. Okay. Now, every time we finish, we always go back up to the root of the tree before looking at the next entry. So now we're looking at the number 13. I'll just try to keep the colors consistent here. We start back up at the root. Are we less than 10? No. We're greater than 10, and there's nothing right now greater than 10, so we're going to have an opening here, and we can put the number 13 right here. Okay. Then we look at the number 4, and we try to find the right place for the number 4. So again, we start at the root. You're less than 10, you're less than 5. So we're going to have to go down here, put the number 4. Okay, now we're going to keep doing this, working our way through the list, always moving back to the root of the tree. Right, now we're looking to find where number 17 would go. Are we greater than 10? Yes. Are we greater than 13? Yes. And we don't have anything currently greater than 13. So we're going to be able to put 17 over here. Okay. Now we look at the number 12. We're going to move our pointer back up to the top. 12 is greater than 10, so we're going to go to the right, but it's less than 13, so we're going to go to the left. We're going to put the number 12 right over here. Okay. And now we've got one last number to consider, the number 1. Go back to the top. 1 is less than 10, so we're going to move down here. It's also less than 5, so we're going to move down here, and it's also less than 4, and there's nothing down there that's less than 4, so we're going to put the number 1 over here. Okay, so we have a binary search tree. Depending on the order we got these values, we might have a completely different tree with these same numbers. Okay? Now this is what we consider to be a balanced tree because the leaf nodes are no more than one level different. Right? These are at level, this is level 0, 1, 2. This is at level 3. So there's really very little difference. We don't have one really long branch and a bunch of really short branches. But maybe if we started with a list already in order, we would have a much longer tree. And the shallower the tree is, the less comparisons it would take to search for something. Right? Because now if you were looking for an entry in the tree, like let's say you were trying to find the number 14 in this tree, right? You would start at 10, and you could say, okay, well, I'm bigger than 10, I'm bigger than 13, I've gone too far, it must not be in there. Okay, and it only took 3 comparisons really to figure that out. Right. Now if we were looking for the number 8, right, it might take us a few more comparisons. We go back up to 10, we're less than 10, but we're bigger than 5, and we're bigger than 7, and there's nothing down here. Okay, so once you have a binary search tree, it becomes very efficient to work through. Doing one by hand, we probably wouldn't go any further than that. Maybe a few more entries. You might see some a little bit bigger than this to do by hand just to kind of get a sense for it. But in general, you won't be doing too much of this by hand. Anything larger than this, you'd be writing a computer algorithm to do. Okay. Now, if you get into more programming classes, you'll talk about how you would delete nodes from a tree. Right? For example, if I wanted to delete this node, that would be very easy. Right? I could just cross it off, it's gone, no problem. Right? The tree's still okay. If I wanted to delete this node, I could just cross it off and just sort of reconnect the 1 to the 5, and I wouldn't have any problems. Right? What would happen if I tried to delete the 5? Okay, well, if I delete this, I can just sort of put the 4 up where the 5 used to be, and I wouldn't have any problems. Okay. But what if I try to delete this 10 here? If I try to delete this 10, and my solution is to move the 5 up here, right? Well, 7 would be the right child of 5, and so would 13 have to be the right child, and you already have a left child of 4, we'd have a little bit of a problem. So if we tried to delete 10, we couldn't just move the 5 up. So there is actually a whole strategy and an algorithm to deleting and removing nodes from a binary search tree. What you do is you try to take the closest thing to the one you're going to delete by either going left and then all the way right, or by going right and all the way left. So if you did want to delete the number 10, then what you'd want to do is either go left and right down to here, or right and left down to here. And either one of these would be a good replacement for the number 10. If you took the number 10 out and put the number 12 here and remove this one, you would still have a perfectly fine binary search tree. This was the smallest one bigger than 10, so if you put it in 10's place, everything else over here should still be considered larger. Okay, so it gets a little more complicated. That's for another day's lesson, but really we're just talking about building binary search trees here. Okay. When you're done, just sort of make sure that every parent is bigger than the left, smaller than the right child, and that happens recursively throughout the entire tree. All right, give it some practice and you'll get better at it.